welcome. My name is Kara Ripley, and I'm the Adult Services Librarian here, and we're so happy to have you here. This is a Badger Talk. So tonight we have Carsyn Ames, who's here through Badger Talks, the Speakers Bureau for UW-Madison campus. So for more information on this great resource for the state, please go to the website badgertalks.wisc.edu. So just before we get started, the restrooms are just outside the door and around the corner. If there are any questions, we will have time for questions at the end. And otherwise, that's all I got. I'll let Carsyn introduce herself as she knows more about it. So here she is.
Cool. Yeah, that one. All right. Is that loud enough? How's that?
A little more? We'll get there.
I can just hold it.
Would you rather hold the microphone?
This one's fine.
Okay.
All right, cool. All right, well, thank you guys for coming. So I'm Carsyn Ames. I'm the curator for the Wisconsin Geological and Natural History Survey. I have a kind of a fun job, and I appreciate you guys giving up a nice summer evening to come hear me talk about it. All right, so first off, if you haven't heard of the Geological Survey, we are a part of UW-Madison's Division of Extension, and pretty much we are in charge of the geology of the state. And the main way we do that is we make maps. So up here I have two examples of recent-ish geologic maps. This one here on the left is from southern Dunn County, I believe, just south of Menominee, and it's about a month old. Is there any way they can turn the lights down so it's more visible? Sure. This is going in and out a lot.
Sorry, we'll get the sound figured out.
Sorry,
here.
yeah. Is that, I don't know.
Well, I think so. Go on, let's see what we got.
Okay. Maybe if I just talk loud, it'll show up. All right. So, little background about what you're looking at here. So these are bedrock geologic maps. The one on the left is from southern Dunn County, so kind of western Wisconsin. And then the one on the right here is from Jefferson County, so just one county to the east of us, and we're over here in Dane County. What you see here is if we were able to scrape off all the soil, all the sediments that the glaciers left behind, all the way down to the hard bedrock, and then kind of bird's eye view flying over the landscape, this is kind of the outline of the different rock units that you would see. Just kind of idea of scale, the map on the left is probably 50 to 70 square miles, and then the one on the right is county scale, so like 550 square miles. The version on the left, the smaller version, it might take us 1 or 2 years to make that kind of map. The map on the right is kind of an iteration of 4 or 5 of the maps on the left put together, and that might take us 4 to 5 years to put together. And so we'll circle back to the Jefferson County map at the end as an example of one way people use our collections to kind of do geology and do research. All right, so this is the very glorious building that I work in. It's out in Mount Horeb. Our main office is in Madison, but the collections and the big warehouse is in Mount Horeb. So it's about 16,000 square feet, and if you're thinking kind of Amazon for rocks, that's pretty much what it is. We moved to this building in 2005 from the Kenilworth building in Milwaukee, and at that time it was about 60 semi-truckloads of collections. So that's gonna be rock cores, rock cuttings, hand samples, and at that time it was all the geologists on staff, everyone on staff, go palletize all these boxes, put them on the trucks, take them off the boxes, put them on these new shelves at the new facility. Somebody write it all down and put it in the database. So it was kind of an all hands on deck situation. When they moved there, the building was about 75% full of storage capacity. Now we're pretty much bursting at the seams. So hopefully a new building is in our future. And then I'd just like to, fun fact, this used to be the catalog call center for Gimplers. So there's a room kind of in here in the building, and along the wall there's about 30 phone jacks. All right, so if we went inside, this is what you would see. Kind of like the library out here, right? So there's these aisles with, instead of books, we have these boxes of rocks mostly. You can see they're stacked pretty high, so we need a forklift to go up there and get the boxes on the top. Each of these boxes holds 10 feet of rock, and then you can kind of see here on the right-hand side and on the left-hand side here, these metal containers, and there'll be these little spice jar looking things, and those are going to be our water well cuttings. And then back here in the back in these wooden shelves, these actually wrap around pretty much the entirety of the building. This is where we store our hand sample collection. All right, so we'll talk about kind of those three big collections. I'll tell you about the collections, we'll talk about how we collect them, and then I'll give you kind of a use case scenario at the end. All right, so starting out with the core. So if we open up those boxes, this is what you would see inside. It's about 10 feet of rock. So there are these kind of cylinders of rock, and what we do is we'll go out and collect them, and then we'll kind of put them in the boxes and then take them away to have in the archive just as like kind of a permanent record. And then sometimes geologists will come, like geologists on our staff or geologists external, like maybe at a university or another state, they'll come and we'll pull out the cores and we'll set them all side by side so the geologist can see the rock record as you would go down into the subsurface. So we have a lot of these. If you took all of my tubes of rock out and laid them all end to end, it'd get you from about Madison to Milwaukee. And then you can kind of see here on the right-hand side the distribution. A lot of people, everyone's always curious about the distribution. It's kind of random, but kind of not. So this Bayfield, Ashland, Douglas area, all those dots, about 80%, 70 or 80% of our collection are cores that were donated from mining companies that went out of business. So this is one mining company's kind of area where they were interested in. You can see these kind of parallel lines that happen here. Those are from mining companies who had prospects looking for sulfides. So those are called volcanogenic massive sulfide deposits. Other places that are fun, this is Jackson County Iron Mine. That's a big reservoir now. Down here in Milwaukee, these are all the cores from the Deep Tunnel project. When they were redoing their stormwater system, they drilled a lot of cores to try to understand if the fractures in the bedrock were kind of predictive or not, and how best they could engineer around those. These kind of lines into Grant and Iowa County, that's Highway 151 improvements. And then most of these other dots that kind of fill in around the state are cores that we've drilled for our own mapping projects. So we've done a lot of mapping kind of in this part of the state, and so a lot of those cores were drilled in support of mapping projects. All right, so this is the other fun part of my job, is every year I might spend 2 or 3 or 4 weeks collecting a new core. So this is like, it's kind of a big deal and it's big business. We might spend like $60,000 to $80,000 collecting a new core. So that's part of the reason why we collect it and we don't want to throw it away. Like, we spent all that money and time to get it, we should keep it. But this is kind of the setup. So usually I'll be in the bottom of a quarry and this big truck will pull up, and 2 or 3 guys will jump out and they'll start getting set up. So there's this big engine, and then there's this mast that goes up in the air, and then you can see there's one example of this long pipe down here. So what these guys are gonna do is they're gonna take that pipe and use this long mast and push it into the ground and then collect my core. And when it comes out, it's gonna look something like this. So this is an example you guys can look at. What they're doing, if we're able to like cut into the earth and see what's going on with that big mast, so there's that big pipe in there, and depending on the setup, there's a series of smaller pipes within the pipe. They call them sleeves. And so similar to a drill that you might use at home, like a power drill, like we're turning and churning, except very different from the power drill at home. I don't want you to crush up my rock. I want to keep the rock. And so our drill bit has a big hole in the middle, and that hole is where the rock's coming up. So if you think of a donut, we're like cutting a donut, but we're keeping the donut whole. And so you can see this bit goes down here at the very end, and these they look green on the screen. They don't look green in real life. But these are industrial grade diamonds, and we use diamond because if you remember like Geology 101, diamond's the hardest mineral. We can use it to cut the other rocks. So they very smartly decided, you know what, we should put diamonds in there, and hopefully that cuts through 90% of most of the rocks that we drill through in Wisconsin. All right, so those guys are all doing the labor and hauling the pipes, and then they get the core and they put it in this little tray for me, and then they bring it over to my workstation. I say thank you, and then I start doing my job. So kind of step one is I make a bunch of notes. So you can see my notebook here. So something I might do is measure how much core we got back. There's a lot of different sizes of pieces in here, so I might record, you know, came out broken, or it came out in one really long piece. That kind of information is valuable. And then other than that, it's mostly just putting it away into the boxes and making sure you're putting it in the correct orientation, because we want to know which way is up. That's really important. And then we'll take it to the warehouse, and usually for our projects, one of the geologists will come out and they'll study the core, and they'll create something called a geologic log. And I have a little bit of an example of one down here. Can kind of think of it as a bar graph, but it's turned on its side. So we have all these columns, and they're all telling us different things, kind of characteristics of the rocks that we use as geologists to communicate with each other. So the geologic logs, they will usually start with 0 at the top of the log, and then they go down below the ground surface. So this is just part of one of the logs. And these 2 columns with the words, it says Galena and then Dunleith and Wiselake. These are formation names, so geologists, we have kind of a standard way of communicating stratigraphy. We all get together and agree that the rocks of this character are going to be named this name. And they're really creative, they're usually just place names. So that's kind of denoting which formation we're looking at. And then these colors might correspond to different lithologies of the rock. So it's kind of small, but you can kind of see here in the picture, this area of the core is kind of light gray, and then it gets with all these white pieces, and then it gets really dark gray. So those color changes are actually reflecting differences in lithology in the rock. The dark gray is like really, really shale rich, and then the whiter part, those are actually all tiny little fossils in the rock. And then the lighter gray it's probably getting a little bit more sandy than true shale. So we'll record those kind of observations in our log. And then all these funny symbols there's a variety of different things they might mean. A lot of the ones on this page are talking about fossils. This P is someone saw like a phosphorus nodule. That circle is someone saw like a lumpy thing in the rock. So we all, everyone has their own version of making these symbols. But basically we put these together for however long the core is, and then that's what we use to communicate what we saw and our interpretation with other geologists. All right, so then moving on to the cuttings. So I brought some examples for you guys. So this is our biggest and densest collection from the subsurface throughout the state. So you can see all these dots on the map on the right-hand side. And then for the folks online, this picture in the middle is kind of what the cuttings look like when they come out. So it's usually just these tiny little chips of rock. There's about 12,000 of these dots on the map. I haven't updated this number in a while. And you can see Wisconsin, we're a groundwater rich state. Try saying that 3 times. So a lot of these dots are public wells, or, you know, I have a cabin up north, so I have a well for my home. And then kind of this middle area here in the central sands region and along the Wisconsin River, a lot of those are irrigation wells. So Wisconsinites, we use a lot of groundwater, right? And so where the people are, we're gonna need a lot more water. So you got Milwaukee, Madison, Eau Claire, Green Bay, and then where the crops are, we're gonna need some water. So that's kind of the distribution of these dots in this collection. So how do we collect these? Kind of similar to the rock cores in that we're making a hole in the ground. With the cores, we're really intentional, and we want to keep as much of that rock, we want to collect as much as we can, and we want to keep it as much intact as we can. Water wells, they're just digging a hole because they want water to fill up so someone can, you know, take a shower or drink some water. They don't really care about the rocks. So they're going to use a drill bit that looks kind of like this picture in the middle. This one is really quite worn out, but you can get a sense. There's this cone here, and this cone shape here, and these little nubs, usually they'll be much sharper. So those are the teeth, and what's happening is these cones are turning and spinning, and then the teeth are cutting into the rock, and it's just turning it back up into little chips. And as they're drilling forward, all those little chips are falling down at the bottom here. So what they'll do is they'll use air or water or mud or some kind of combination, and they'll pump that in, and it goes down, and then it picks up those chips of rock and move them out of the way so they can keep drilling and going down. Used to be the DNR required every water well in the state, the drillers take a sample every 5 feet of those little chips and then mail it to the survey. So you can see why my warehouse filled up, and I need a new one. So we actually got with the drinking water people, and we're like, hey, we're like running out of space. This is too many cuttings. And they're like, yeah, all right, that makes sense. We didn't maybe think that all the way through. So I think in 2020 or 2021, we changed that rule a little bit. So now it's some certain number of people the well serves, or we can request for cuttings in an area where there's not many other points. But it has made my life exponentially easier. All right, and then this is just another picture kind of show you how these are stored. So we're really not keeping a lot of material, like it's maybe a third of a cup, a couple tablespoons. And we're just kind of keeping those, and we'll do the same thing we did with the core. We'll create that geologic log, but as you can imagine, for the people in the room, I passed around that piece of core. That was a big piece, and you could see a lot of features. Those tiny chips, like, good luck sometimes. They're so small. Sometimes because the drilling is so like kind of violent and mixes everything up down there at the bottom of the hole, sometimes it's the equivalent of if I crunch up a chocolate chip cookie and give it to you, and I also crunch up an oatmeal cookie and give it to you and say, okay, well, at what point in the subsurface did it turn from chocolate chip cookie to oatmeal cookie? And I have to say, I don't know, maybe like somewhere within 30 feet. But that rock core had nice contacts, and I can tell you, oh, that happened at 20.4 feet below the surface. So while we have a lot more cuttings, the kind of questions we can ask and the questions we can answer are a little bit different between the collections. All right, and then our next big collection that we have is going to be our hand samples. So these are sometimes fist, sometimes head-sized pieces of rocks that the geologists will collect while they're out in the field doing their investigations. Usually they're making maps. This collection is kind of fun because it goes back way back in time. I've been recently working through a lot of the collection from like the 1890s-ish to 1920s-ish time. And these are actually really fun because they all come with field books. So the geologists will be out there, they're making their notes. Usually they'll say, have some kind of location description. They'll say, oh, I was 5 miles northeast of Wausau on the east bank of the Wisconsin River, and I collected sample 2, 3, 4, 5, and here's a short description of the samples. What's nice for me as the curator is I can say, all right, cool, Google Maps, Wausau, Wisconsin River, 5 miles north, east bank, drop a pin. Now I have a lat long. I can put that in the database. I can type up the description, and then sometimes they come with pictures, and I can, scan a picture and attach it. Those samples became way more useful than just sitting in a drawer. So this is a lot of my job, is like trying to make these collections more useful and more readily available for other people to use. So we have all these rocks. They're really old. They have some information. One of my favorite parts about using the archives for kind of our investigations and our mapping, so 1893, plate tectonics wasn't like a concept yet, right? They didn't even, they didn't have like the modern geologic timescale figured out yet. So these guys are doing their best in making really good interpretations based on the information they have. But me in 2026, I can go back and look at these samples and I can pick out a lot more things because we've discovered a lot more things since then. So there's this big push since like early 2000s on kind of a federal and state level of not just geology archives, but like even other sciences like biology, to dig back into these archives that we have and kind of go back and reinterpret some of the pieces that we have using like the updated science that we know now. All right, and then there's just a couple more pictures. So those are those drawers, and then if we open them up, it's just full of rocks. Each of these rocks, they'll have like a little label. They're usually numbers, and then I can go in the database and it'll say, oh, references field book 17. I can go to field book 17, page 12, and I see an entry for this sample. It'll have like a location and a short description, and then we're off to the races. All right, and then our last big piece of the collection, so they take those hand samples. Sometimes what they want to do is they want to cut a thin section to better understand and describe that rock. So sometimes the crystals are just so small in the rock that you can't tell them apart, and we have to make a thin section to be able to figure out what the different minerals are that make up the rock. So same thing as biology class. When you looked at that onion root under the microscope, we can do that with rocks. We cut a really thin slice, put it on a microscope slide. This bottom picture shows what it looks like in regular light, so same as with that onion slice. This cool picture at the top with all the rainbow colors. This is something that we do. We cross-polarize the light. So think about like, was it like Pink Floyd with the prism with the rainbow? Kind of that idea where we're bending the light. We're using that different setup to tell us different optical properties of the rock. So you can see these kind of spaces where it looks clear or like there might not be any rocks or minerals there. There actually are, and because it's clear and we can't see anything in the plain polarized light, we might go to cross-polarized light and then kind of look at these rainbow colors and say, oh, I know that that's whatever, insert mineral because it has these optical properties. So these become really useful for kind of the nitty-gritty and the technical of geology. And then I like to just tell a short story about Florence Bascom. So, like Bascom Hall, that old President Bascom guy, Florence Bascom is his daughter. She finished her master's at UW in geology in 1887, and she went on to Johns Hopkins, and she was one of the first women awarded a PhD there, like at all, in geology. And so she's kind of like this pioneer rock star lady, and she actually like did a lot of the seminal work and a lot of illustrations, kind of developing petrography, which is what we've been talking about, like as a science. So we really owe a lot to her, and she's, from Wisconsin. She went to UW-Madison. She spent a lot of her career working in the Acadian mountain kind of region in the Northeast. But pretty cool lady. If you're going to look up any geologist, I would start with her. All right, and then just another kind of use case and like what I do as a job. So I read this publication that came out right after COVID, and the best I can tell is these couple guys were bored during COVID, and they said, do you think we could scan thin sections on a 35mm slide scanner? And they said, why not? Let's see what happens. And it actually worked out pretty well. So these little slide scanners are like $300 or $400 versus what the big equipment I would use to get these pictures is like hundreds of thousands of dollars. Bonus, this fits on my desk at work. It doesn't take up an entire room. So we put in a grant to ask for funding to digitize like 4,000 of our slides. So advantage including that I can go through into those field books and I can digitize the descriptions of the samples. We didn't have those all digitized before. And then I'm also creating like a digital library of our thin sections. And I was actually able to get the resolution high enough on these images that the geologists came back and they said, wow, these are like, I can do the microscope work without the microscope. That's how good these images are. My boss did not like how big of files they were, but all right. So some more recent work. All right, so I said we go back and talk about Jefferson County. Right, so this map, I think I said it took about 4 years to make. I came in about halfway through it being done when I started at the survey. Kind of my role is, so Esther Stewart, she's the one who's making the map. She's the geologist in charge. And I am in charge of all the samples, right? So Esther says, well, can you help me figure out like what area do we have samples? Are they gonna be useful? Here's what I have so far, here's my interpretations. Can you like help me fill in the gaps? So I'm kind of like the in-between of the researchers and then like kind of interpreting the samples and figuring out what we have. Kind of like the research desk at the library. If you're like, hey, I'm writing a paper on John F. Kennedy, and then they're like, oh, have you seen this book, this book, this book? All right. And then I just wanted to stop and kind of key you guys into what you're seeing here. So geologists, we get trained to read these maps, and they're not intuitive at first. So what you're seeing here with this legend is how the rocks are stacked up on top of each other. So this purple unit is going to be at the bottom of the cake, and then the layers are going to go up, and it's going to start with this kind of brownish tan color. So you can see the brownish tan color here, and then it grades into the blue, and then it grades into the oranges and the purples and the green. So we're starting up high here, and we're cutting down into that bedrock the farther we go west. All right, and that'll become important once we start looking at the cross-section. All right, so remember how I said the bedrock, this is like we scrape off all the sediments, all the soil? Well, Jefferson County has a lot of sediment, a lot of soil, swamp, a lot of farms, a lot of corn. If you've ever driven around out there, it's really pretty. Not great for making a bedrock map because the bedrock is like 400 feet below the surface. Normally we want to see exposures like this, and so we can go out and we can touch the outcrop and we can say, oh, the contact between the upper unit and the lower unit is right here on the rocks, and then I can reference that on a map. Jefferson County, there's like hardly any outcrops. So this is Esther, and she's wondering, how am I gonna make this map without any outcrops? So this is a good case. We have all those dots on those maps that represent samples from the subsurface, right? All right, so this is the cross-section from the map, and I believe it's northeast to southwest. I'll probably just call it east and west. But what you can see here, there's all these vertical lines. Each of those is gonna represent some kind of data set that we have. So when we're on the surface, that's a point, and then we cut into it and we're looking at the side. So now it's kind of a line. So we have either rock cuttings or rock core or just some kind of a record of when they drilled a well of what the different geology and the different lithology and the units below the subsurface are at each of those points. So we'll zoom in kind of and just use kind of the right side of the map or the cross section for now. And then my reminder to point out, just keep an eye on these like There's some of the lines are dashed and some of them are solid, and we'll talk about that in a second. All right, so that top unit, this is kind of that tannish brown color that we saw on the map. This is what that rock looks like. So Jefferson County, I think we had 1 core and we drilled 2 more. So this is the core that we had, and it kind of didn't go very deep. It went through these top 3 units and then stopped. So that core was like medium useful, but this is what it looks like. So it's this kind of limestone with a bunch of shale in it. We call it the Platteville Formation because the type section is in Platteville, Wisconsin. And then the 2 units below that are in this kind of blue color on the map, that's going to be the St. Peter sandstone. So it's this nice kind of white, sometimes iron stained sandstone. And then this dolomite of the Prairie du Chien Formation, which has kind of these characteristic like big white nodules, or sometimes it's chert, but it's usually like really hard and really, we call it massive, like it's not really broken up into many pieces. So that's the Prairie du Chien. So remember how I said let's key in on these dashed versus solid lines. These 2 units have kind of an interesting relationship, and you can see there's a solid line and then it kind of runs into the dashed line and then it turns back into the solid line, and it's not really flat. It looks like it's kind of like hilly, like a roller coaster. So why is that? As a geologist, that strikes me as weird. Well, okay, so Esther and I are looking at the 2 cores that we drilled. I believe this one is from the southern part of the county and this one's from like kind of the central part of the county. And just visually, you guys, like, you can tell me like something, those don't look the same. The rocks should look pretty similar. They're in similar area. They're, you know, the same elevation in the subsurface. So when we drill these cores and when we start to log them and interpret them and kind of put them in context with each other, we get into a scenario like this, and it's a little tricky. And this is like one of the fun, in my opinion, one of the fun parts of being a geologist. You have to be able to go back and forth between scales and time and kind of like keep everything in context together. And so probably what happened was this lower unit, the Prairie du Chien with all this white stuff, was deposited, and then a bunch of time went by and it started getting eroded. And if you guys have heard of karst, we were creating kind of a karst environment, like sinkholes and areas where there's like rigid rock and then like big valleys. And then some time went by and then the St. Peter was deposited. So St. Peter represents this kind of big like beach environment. So think about there was enough time for the rocks to erode and then an entire ocean to come inland and then start depositing like all this sand into all those valleys and filling it up. And so as geologists, usually what we do kind of first pass is, well, is there anything like in the modern environment we can compare to? This is a really extreme example of a karst environment in, I think, eastern China, but kind of gives you an idea of what I'm talking about here. So there's these resistive units that are the dolomite. So this is that Prairie du Chien with all the white stuff. And then there will be areas where it's been cut down and there's these valley floors. So we deposited the Prairie du Chien, we eroded it, and then we're kind of at the point before the St. Peter and the beach comes in and fills all this up with sand. So now you can kind of get a sense of why that line was so bumpy. So we're looking at places where it was more resistive and then it was cut down and then resistive and cut down. All right, and then just a couple more units below that. Next we're gonna have the Trempealeau group, which includes the Jordan sandstone, which is this nice tan, clean, we call it clean sandstone, and then the St. Lawrence Formation, which is kind of a dolomitic limestone, siltstone unit. It's really pretty. It's usually like this purpley red color. And then below that, we have the Tunnel City. So this is another sandstone, kind of siltstone with shale. If you are driving around in kind of western Wisconsin, west central Wisconsin, the road cuts that are like really dramatic and they have all this green stuff in it, you're probably looking at the Tunnel City Formation. It's always really pretty. And then it's really characteristic because it will always have this green mineral. It's called glauconite, but that's like key, like you see the green mineral, you almost always are like, oh, Tunnel City. And then below that, we have the Elk Mound group. So we're back into some nice white, clean sandstone. These are really kind of coarse grain sandstone. And so the coarser the grain sandstone, the bigger these grains of sand, and the more water I can fit into all that space around those grains of sand. So the Elk Mound group is one of the main aquifers for the state, for groundwater aquifers. So a lot of, like especially like the municipal wells, they'll drill all the way down to these sometimes 1,000 plus feet to get to this aquifer to supply water. All right, so we did all those observations, we had all those points, so now we pretty much are just gonna play like connect the dots, make a cross section. So this is the area we kind of started with. We'll add some more points. Draw our lines across. Pretty good cross section, pretty good interpretation. What we'll do is we'll kind of make that interpretation, go back to the original map, hold it up against the map, make sure we didn't put any units up higher or lower than they needed to be, make sure they match what we saw on this surface. And then we'll say, hey, we finished it. Everyone on the project signs off. Everything goes to peer review, and then we'll get comments back, fix a couple things, send it to the editor, and then it gets published on our website, and then the public is free to use it. All right, so if you didn't get enough, there's like a short video tour of the repository as well. You can just Google like Wisconsin Geological Survey repository, and I'm sure you can find it. It's on YouTube. And then other than that, just reiterate, Badger Talks is a pretty cool program. There's like all specialties of speakers. There's probably 10 geologists, but I've listened to the people from the Historical Society talk about the dugout canoes, like they're part of Badger Talks. There's all kind of different speakers you can request, and we do it for free. But with that, I will take any questions. Yeah?
So on those maps, it really needs to be three-dimensional, right? Because you go down 300 feet, it's a whole different map than if you go down 700.
Yeah.
So what is the map that telling you the majority of the rock in that area is this kind?
Yeah. So kind of thinking 3D about the geologic maps, and when we're looking at what we draw, it's easier, in my opinion, when I think of it, is that's like one elevation. So that's like if we just cleared everything off and it was level, and then we'd see like all these like craggy areas. But mapping in 3D is like the hot new thing. We just finished a publication where 7, I think, southwestern counties in the state where we basically did that. So someone took like all of the data that we could get our hands on, and they kind of made a 3D model of the subsurface. And then my part of the project was I went out and found areas where the rocks intersected with the surface. Like I just drove around and found where different units were in contact with each other, and then recorded that elevation so they can ground truth the model. But yeah, 3D is like the hot new thing.
I was expecting you to plug the Rock D website.
Oh yeah, that is the geoscience department. Someone in there, that's his thing. But that is a fun app.
Yeah, so basically it'll tell you what the rock is below you,
Mm-hmm.
anywhere you are.
We have something online.
No, well, I
Okay.
have a question.
Okay.
So it took like 4 or 5-ish years to do the maps that you were showing. And then how frequently are they reviewed? Like if you get additional core samples or other information, they then, is it just like reiterative? You keep going back and making them
Yeah, that's a good question. So we make the map, and then we get more samples, more ideas, more data. I guess like a 200-year cycle since I'm looking at stuff from 1890. But no, that's a good question. I would guess we wouldn't remap anything that has been done within probably like the past 70 years. Just, so like people, there's development, they move roads, they blow up rock cuts, they close mines, they open other mines. So over time, like there does become new data. And unless there's like something glaringly wrong with what we did the first time, it probably wouldn't be worth the investment to like redo the whole thing.
So do you have like engineers discussing with you ever or consulting you about, building a huge skyscraper and how much weight is going to be tolerated in an area based on the type of
That's a good question.
and the levels of consistency going down, supporting it?
So we're thinking about engineers and do they listen to the geologists about what's below their feet? So my husband's an engineer, so I would say no. But no, but they do use our data kind of preliminarily. We're like, because we're state, so we're such a big, broader level than them, they're usually working at like a site level and they really want to understand like in this room what's going on. So a lot of the engineering people, like whether they're building roads or buildings, they will just take their own samples to however deep they need to go. If they need to go to the bedrock, they'll collect their own samples. And then a lot of what they do is they'll send stuff out for like strength tests and how much water is there, and then they'll turn that all into numbers and then do all their calculations. So sometimes, but we're just like so much broader scale than they are. That's okay.
I was also kind of just curious about like the earthquake thing. I mean, I know there's been some very mild earthquakes in Wisconsin and how that would interface with the bedrock stability, and just curious if you.
Yeah, earthquakes are kind of hard to explain in the middle of the continent where we're at. So earthquakes happen along faults in the subsurface, so there's kind of like a place where the rocks have like split apart and they're able to move past each other. We just don't have a ton of these like big, large scale ones in the Midwest. The one that happened in Lake Michigan, that's like by Midwest standards, that's a pretty substantial fault system that dives down there below the lakes.
Yeah, I don't think I was there.
Yeah. Mm-hmm.
On that cross section of Jefferson County, you're showing that like a lot of the cores like they go all the way to the bottom.
Yeah.
How do you know what's below the layer that you can't drill?
Yeah, that's a good question. So we're talking about the cross section and how these don't go all the way down into these layers. So how do we know what's going on below the surface where we don't have those points? So this is where Esther is a better geologist than I am. So she can start to pull in other types of data sets. So one data set that we rely on pretty heavily to understand these, I don't know, what color is it on the screen? Brown and purple units. So as geologists, we call this the basement. This is like the crystalline rock, like way deep, that kind of holds up all the continents. What Esther does is she looks at a data set that they gather from geophysical methods. So they'll like kind of fly this airplane and they'll pick up either like how magnetic are the rocks in the surface, or like density, that kind of stuff. And she's able to like interpret and work with that data set and understand where where does it go up, where does it go down, what the rock is made out of, way above my pay grade. But basically the short answer is we just start to incorporate other data sets that we have. And a lot of it too is it's being a good geologist and being able to make good interpretations. So like these, where it has COPG, these really thin pink lines, That is the Parfrey's Glen formation, which is like Parfrey's Glen and Baraboo is that big with all the conglomerate. Esther's able to like look at all that data, synthesize it, make an interpretation, and understand that even if we don't have a point touching that unit is still there in the subsurface, like with enough confidence that she put it on the cross section. Mm-hmm.
How's the driftless area complicate things?
Driftless area is easier, in my opinion. There's a lot more outcrops. Driftless area is also easier, well, kind of the whole Midwest. The rock layers are, because we don't have any of those faults and nothing's happening, no mountain building events, so everything's kind of flat lying. So it's really easy to make a map when everything's flat. Mm-hmm.
So the naming conventions, I heard you, there's like the Prairie Machine one, is that standard in geology to localize a naming scheme?
Mm-hmm.
So you visit a different region and they have,
Yep.
funny names, I guess?
Yep. So stratigraphy, usually every state survey, so most states have a state survey. State surveys will kind of publish a stratigraphic column, and that's that kind of standardized way that we all communicate. But doing the names and stuff, there's a congress. Like, there's a group of geologists who are like, we're in charge of the naming schema and stratigraphy as a whole. And there's like, if you want to change the name or you want to like add more names or combine the units, you have to, there's like 9 pages of rules you have to follow, and you have to write a publication and make like a clear case for like why these changes need to happen. It's like so contentious and it's crazy. And then it's even crazier, so like our stratigraphy does not have to match the stratigraphy in Minnesota, even though it's the exact same rocks across the river. So we're the state geological surveys, the federal geological survey, that's kind of like one of the big reasons why it's important that they exist. So they're able to like kind of reconcile those differences, and then I think they finished the like national geologic map. So they spent a lot of time like, okay, well Minnesota's calling this rock this, and Wisconsin's calling the same rock something different. How can we like get those all lined up on a map? But yeah, stratigraphy is like a crazy subspecies of geology. Mm-hmm.
Would you be able to tell on that map where the water table will be based on the layers?
That's a good question. Yeah, so where is the water table? We can kind of see, right? So Esther labeled the rivers, Lake Ripley, and then this grayish line is the land surface. So yeah. But yeah, a lot of what we do is, so we have probably 5 or 6 geologists, and then we have probably 3 or 4 hydrogeologists. So they're the people who would come on here and say, oh, well, the water level was at this level in this well, and it was a little bit lower here. And so they'll come through and they'll draw stuff like the water table.
I noted that young grade school kids may not be able to do what you do because they don't read cursive anymore.
I know, right? Okay, I gotta go back. So I've been doing this for like 2 years. This is an excellent handwriting. Like a lot of the time it's cursive, but it's like, you're on a horseback and they're like riding and I'm like, I can't even guess what this says. But my mom is an English teacher, so I'm like, yeah, she made sure I knew how to read cursive.
Just end up using AI to
Yeah.
read it.
So much of what you talked about today really depended on large, heavy equipment and technology, and you're talking about the database and scans. And so it does make sense that it has really pushed forward the scientific understanding of rocks and all of that. How much of this could have been done with, like you said, on horseback, and like how were the first samples collected? Was it just like on the surface, or I guess when did it start getting so complicated?
Yeah, so there's a lot to unpack there. So like, how did these guys do this back in the day? James Hutton, like, he really spurred geology in like 17 something. He's a Scottish geologist. Just walking around and seeing like what's happening on the surface of the earth now, and then seeing rocks, like strata outcrops, and then being able to say, oh, that made the sand pile up like this, and then I see the rocks have sand piled up like that, and making those connections. And so they like do that, and then over time, you do that more and more and more, so you get more details, and things can become more sophisticated. So that's all like at the surface. And then you start like hand digging wells and like pulling up rocks from, in the 1893, these samples, a lot of them are from just hand dug wells, so it's maybe 30 feet down into the surface. But the rocks like can change within like the 0 to 30 feet below the surface. And so just being able to like access that rock and being able to like maybe lower yourself into that hole and see what they look like in contact with each other. Yeah, it's just like learning history. Like the farther we go, the harder it's going to be to like learn all of Earth's history, like and people history. I don't know. I don't have a satisfying answer.
No, that's helpful. Thank you.
How many or how much of your sample collection, like the hand samples, you can't really make that available as online as data? I mean, you have photos and weights and three-dimensional images of the actual sample?
Yeah, so that's a good question. So we're talking about kind of how do I make all these physical things available online or digitally or to people far away? So like a small step is what I've been doing, where I look at the field notebooks and I like type it. So now it's searchable, and then I'm creating like a point location. So now it's searchable in the way that geologists look at data, like spatially. So that's like 20 steps forward compared to it just sitting in a drawer where nobody sees it. There are like some state surveys. I think Michigan got this scanner that can like scan stuff in 3D, and then you can like play with the rocks in 3D, so you can start to do that kind of idea. I don't have the expertise for that yet, so maybe one day. Mm-hmm.
Question for the very thin samples.
Mm-hmm.
What are we using to cut those? Is it water or?
Yep.
Okay.
Yeah, a really thin blade, as thin as you can get it, and then it's just water cooled usually. Sometimes it's oil cooled if the sample's like really crumbly.
Is the light refraction used on the thin sections the same or similar to what like jewelers use to identify unknown gemstones, where they get like, oh, it refracts at this amount, so it's higher or something like that?
It's like similar properties. I don't know if they're cross-polarizing the light or just diffracting it, but it's the same idea that different minerals are going to behave differently, and so you can identify. All right, well, thanks for having me.